you want to pop in?
You got a question?
No.
Oh, okay.
How do I submit a question?
Well, as you raise your hand, I may or may not see it in the dark. Otherwise, we'll just get started since it's slightly past 5:30 now. So, DakotaCon CTF, I've already talked to you about it once. Here comes again. Public source challenges. Create as many as you like. You can still compete. There's a Slack channel. I hope you can hit that if you want to join. DakotaConCTF.slack.com. There you'll get like the directions on how to create challenge and any other stuff that you might need. Cyber Conquest, same thing as usual. Make a team, compete. Cyber Conquest.
We're making fun machines.
Yeah, I've heard some goodies about some of these machines. It'll be a fun time. Spring break is coming up, so let's do a CTF to start it off. The UT CTF, so University of Texas or something, starts on Friday, goes to Sunday. We have a DSU team right now. I'll post the creds in CTF again. I think I did it like 2 weeks ago. They're gone now. It's going to be a wide range of challenges. Like they're easy to hard. So if you want to try and learn something new, I think the more advanced people will probably jump into the hard ones. So we'll leave the easy ones for the newbies. Not to call you a newbie, Gib, but not sure how much advanced exploitation stuff you know.
Bro, I feel like you love it.
There's no limits to the number of players we can have on a team, even though like their site says that, but it's wrong. I've already asked them. So when we get top place, we get prizes for our school. So then let's try and do that. It'd be pretty cool.
T-shirts?
No, maybe. I'm not actually sure. They never said.
Oh, what day must I get a T-shirt?
Okay, but just saying, we still got to get top place for this. So current events. Chris, do you want to talk about that or you want me to ramble?
Do it from there.
Okay, I'll ramble. Strategic Cyber is a company, I think.
Go for it.
So, Strategic Cyber was bought by... Okay, so there's like a little bit of less detail in here than I was thinking. This is the Cobalt Strike one though, isn't it?
Yeah.
Okay, so if you guys didn't hear, Cobalt Strike, hacking C2 kind of infrastructure, was bought by Strategic Cyber?
So no, Strategic Cyber is the group that made Cobalt, or that manages Cobalt Strike.
Who are they bought by?
They were purchased by Help Systems.
Help Systems, right
Which
here.
is a Minnesota-located company.
Okay.
But that company is also the same one that made Core Impact, if you're familiar with that. It's kind of like a suite of tools, if I remember correctly. So that's the thing.
Okay, so like what I've heard about this though is that they're still planning on continuing to work on Cobalt Strike, so they're not stopping by any means. So like maybe this could actually be better. They might have more funding or backing to actually add more features to it, or it could be behind an even bigger paywall than it already is because it's not a cheap tool to buy. Have I been pwned?
So there was, so for a while, this is like it's been open like for sale sort of thing, and then I guess like the news is that he's like, actually I'm going to keep being independent. We're not going to sell the service
Oh, that's nice.
to a company or whatever, because he's like, I don't think the best way to manage it is just for an individual to keep it up or something, or I don't know. He didn't want it to end up being consumerized.
That's pretty cool. So I think like if it was consumerized, it'd probably be like, hey, your company was just leaked. We may or may not have their creds. We could post them, or you guys could pay us, and now we're not going to talk about it.
Yeah.
It's like, I think this is a better way. Let's Encrypt. I heard a little bit about this. So as of today, right?
Yep.
As of today, they revoked 3 million certs for sites. That's actually that's a lot.
I tried to like put how it works on there with like a nice little text drawing of a server and several domains pointing at it.
So I'll try. So for those of you who don't know what a cert is, the cert pretty much just is what's used to encrypt the data that's sent between in the traffic and HTTPS and the other secure kind of connections. So each cert is kind of set to a specific cert is kind of set to a web domain. So like each web domain has a different cert. So like you can't decrypt someone else's traffic with a different cert. But having 3 million certs revoked is a lot because that means 3 million sites now are certless, or say they're not secure, which could hinder traffic and profits. And that means they also had to get 3 million more certs, which I guess it's not too hard to actually get a cert, but what's this down here about?
So this is my understanding of just quickly reading the article. I might be very wrong, but the issue I think was that with like the checking of the domains, so you'd go to like it would, if you have several domains on one server, so the software was having an issue where it would only check like the first domain or one domain over and over and over for like n amount of domains that you had for the server. So if we had like 5 domains, it would check that first one, verify it, and then just be like, yep, it's good, yep, it's good, yep, it's good. So you can have all these domains that are certified, but DNS, which has to be updated, like the CAA records have to be like updated and checked like beforehand sort of thing. They weren't being updated, so you had a bunch of certified things that weren't backed up by DNS. So it was this weird error, and for whatever reason, the only way that they were just like, the only way to fix this is to straight up just like revoke certs or have people like redo the certs correctly. So it's not as big of a deal if people like get on renewing their certs, but it's still kind of a big deal because I'm sure that like somewhere in that 3 million people aren't going to be on the ball.
Yeah.
They sent out emails and everything, or like for like whatever you registered with through your email, but I'm sure that since Let's Encrypt is this like kind of sketchy, almost like free to register sort of service, that a lot of people probably didn't put a legit email. That's my guess. Yeah.
Do you know if the Let's Encrypt cert bot, like if people who have it set to auto renew, if it's just automatically is going to renew now, or if it's going to wait till the end of the cycle or something?
I'm not sure. I can post there's a curl command that you can run for your domain to see if it was affected.
Okay.
I can throw that in OffSec.
Yeah.
And then you can probably just delete whatever like subdirectory has the like current keys in it, run certbot, renew, and it'll kick off. Or actually, you probably have to go through full process again, but
It's not too hard.
no.
As of today, PowerShell 7 was released. That's it about that. No one cares about PowerShell.
Yeah, PowerShell!
So today we're going to talk a little bit about assembly and then go into a little bit about actually how to reverse challenges and other binaries. So to actually understand it, first we have to talk about what assembly is and kind of understand what's happening. So here's just a little program I wrote that just pretty much does a scanf. But as you can see, they both look kind of different. On the left is an Intel syntax for X64, I guess, but for Intel. And then on the right is an AT&T syntax. Doesn't look nearly as nice and has percent signs flying everywhere for some reason. So just try and avoid these as much as you can, and we'll all be better. So what is assembly? For those of you who don't know, machine pretty much only, or your computer only understands like ones and zeros for the most part. May understand something that people refer to as machine language, which is like really low level below assembly, but we're not going to really talk about that. But the problem is we can't understand ones and zeros like easily. So like we need something that help us become a middle point between our high level instruction, our high level languages, and then what the machine actually learns or understands. And this is where assembly comes in handy. So it's the middle point between our high level languages like C, Perl, Python, pretty much anything. So we're going to start talking about x86. So this is kind of this is all pretty much Intel processors. These are for mostly personal computers and laptops, but nowadays like AMD is starting to challenge that, where they want to start coming into the personal computers and servers kind of setting. But Intel has this predicament where they have 981 different instructions, and where most of people don't actually know or won't use more than 50 at all. And even a compiler won't use most of those instructions. So like that's where Intel kind of has downsides, where there's all this useless information that might be slowing down a processor, while if we just kind of got rid of all of that to make it faster. So that's kind of where AMD steps in. We'll talk about that later. But for x86, the number of bytes per instruction, so how much space each instruction actually takes up on like the processor and in memory, can range from 1 to 15 bytes. And then another little side bit is that there's 15 registers in x86, but we can only really interact with 8 of them. And that's not really that much, but it's enough to get done what you need. So here we'll talk about ARM. So for ARM, most phones or embedded devices will run ARM, so like small devices, but as I said earlier, more servers and home systems are starting to become ARM-based. And they actually implement RISC-V, which stands for Reduced Instruction Set version 5.
Computer,
Is it computer?
I believe.
Oh, yeah. But anyways, it's version 5 of whatever they have, which means they only have actually around 50 instructions, which is a huge difference to the 900 some, right, Gib? Yep. So, in ARM, in 32-bit, all instructions are 4 bytes aligned, no matter what it is. They all take up 4 bytes in space. They have 37 registers and only 15 you can use. This is where I kind of don't like ARM. It's like, this is how they name the registers, R0 through R15. So who can tell me what R13, 14, 15 actually do?
Parameter passing.
That's right, R13 is the stack pointer. R14 is the link register, I think. And then R15 is the instruction pointer. You wouldn't actually know that unless you did some ARM. I think, is that right, Zach?
What's that?
Yeah, it sounds right. So we'll go back to, because we're going to talk about Intel pretty much only. If you will, we could talk about ARM, but I'm not as experienced in it. But so this is kind of what 32-bit registers will look like. We have an EAX, an EBX, an ECX, DX, SI, DI, and then we have some stack stuff. And then we can also split those up into different chunks. If we want to grab the 8 bits of the lower chunk, or we want to grab the 16 bits, we can grab by AX. So this kind of makes it handy to make 16-bit and then 8-bit previous versions backward, or make current systems backwards compatible with old systems. And they're just a handy way to interact with systems. Oh, so I'm not sure if it's like obvious, but like this whole register is 32 bits then the lower bits of AL are 8 bits. Yeah. So we'll get into the stack and like calling convention. So what I'm currently thinking is I'll just try and give a quick run through, and then we'll actually try and get hands-on stuff. So it's not just me preaching to you guys. We'll actually get to learn something that's useful besides me just talking. So we'll get into like talk a little bit about the stack and calling convention. So when a program calls a function, we have to be able to find a way to pass in parameters to that function and then get back to where we currently are in our program. So this is where we're going to use a stack. Does anyone not know what a stack actually is? Because I can talk about it. I'll talk about it anyways. So the stack is kind of an area in memory that allows for addresses to be stored or data to be stored in a like kind of way you would stack pizza boxes, I guess, one on top of each other. Like that?
For pancakes.
Pancakes.
Straight pizza boxes.
Stack of pancakes? No, stack of pizza. Come on.
Wouldn't download a car.
But anyways, so what this kind of means is we need one register to point to the top of our current stack, and then another register to kind of save the top of our previous stack. And this is where ESP, our stack pointer, and then EBP, our base pointer, come in handy. So I'll kind of run down of what's actually happening right here. So like if we were to do this printf right here, we need each of these to be pushed onto the stack separately. So let's say we call printf. We need to now push on, we actually need to go backwards through the argument list to push onto the stack. So we'll start with the integer that we're going to push on first. So parameter 3 would be integer. Then we'll push on the second, so string, and then the third, the actual format string that's going to be called. And then after that, we need the return address. So this is important so we can jump back, like I said earlier. And then we'll save EBP, because what if this function now calls another function, and we just keep kind of moving down. This is kind of referred to as a dynamic stack, something like that in OPSES, don't worry about it. And then if you have any local variables, they'll kind of be stored above the current EBP state. Saved ESI and EDI, those don't really happen too much, but they can happen. But why this is important? This is important because now you can grab your local variables either off of EBP or ESP, because they're always going to be in the same spot on the stack. They shouldn't move. So you should be like, hey, grab me the first local variable, that's EBP minus 4, and so on. So we'll talk a little bit about X64, so like the 64-bit version of Intel instruction set. So instead of actually pushing it straight onto the stack when we call a function, we're first going to push into register RDI, then RSI, then RDX, CX, 9, and 10. We had some more registers added in the 64-bit version. We had, I think, 7, 8, 9, 10, 11, 12. Don't quote me on that, but any more, but like if you have any more arguments, but 6 arguments is a lot. Any more than 6 arguments will then be pushed onto the stack, kind of the same method, but you don't really have to worry about that too much. And here are some common instructions that you'll probably see. These are like the most common. So you'll see a move, an add, sub, LEA means load effective address. We have a push, a pop, a return, some multiplication, division, comparing. So like if you want to say is something larger than this, we'll use compare, and then a jump, so you can jump to a different address. Now here's some bitwise operations. So if you don't know what bitwise operations actually do, they interact with individual bits of the memory. It's like we have rotate right, rotate left, just kind of moves the bits around. Same with shift left, shift right, and then and, or, XOR, not. So I kind of like sailed through that pretty quickly. So I'm actually going to do some hands-on reversing so you guys can kind of see my thought process when I see a program. So I've got 2 here. I've got IDA and Ghidra. Is there a specific one you guys would rather have me use?
Ghidra.
Shows that pro license.
I don't have it yet.
It's
Ghidra?
like the black badges for.
No, I actually got email like yesterday saying we're almost ready.
Oh,
Okay, so
okay.
go over
This is
Ghidra.
large,
Let's see which one. We can go over. So I was looking up for some reversing challenges to actually go over, and the problem with most reversing challenges is that they're not actually x86 or x64. They're actually a different language that they want you to reverse, like that convolutes it more. So like a Go binary may be compiled to x64, but the way it calls functions and handles memory, it looks really disgusting, and I wouldn't want anyone to actually deal with it. Same with like Rust or Python. It just gets really gross. So something that I actually found is that pwn challenges, you actually need to reverse those to figure out what's going on. So that's why I'll kind of go over is just some different pwn challenges that I've seen. And then we'll go over those to see what we're actually looking at. We might talk about the vulnerabilities, but it's more of just trying to figure out what's actually happening within the program. So we'll start with lab, not IDA, Ghidra.
Carnegie Mellon still has their old binary bomb labs up.
Oh, really? Maybe we'll just pop in one of those.
Probably just searchable, like CMU binary bomb.
CMU binary.
It's pretty old.
Oh, do they have like a repository of binaries?
So it's sounding like. That was a PDF. Nope. If you can find that queue, send it to me and I'll bring that up. But anyways, we'll hop into lab is from, I believe, our Hack the Box CTF qualifications from November. We have a write-up about it, but Jared actually did this challenge and not me, so this is kind of my first time actually looking at it. So the thing with Ghidra is that we all should probably know it comes with this nifty decompiler. That's kind of small, but it says decompiler. So it just pretty much means is it'll try its best to actually figure out what's happening for you. It's like here, that's pretty good That's pretty good telling us what's actually happening. But if we went to the assembly, not so much. So you guys want me to look at both of the decompilation or just the assembly? So like this is assembly day kind of.
Whatever your workflow is.
My workflow? I kind of prefer IDA instead of Ghidra. It's just that sometimes Ghidra's decompilation kind of looks a little gross, but right here it looks pretty clean. But if I was doing this here, I pretty much just mainly look at the decompilation. So what looks like we're taking this first variable off the stack and tossing the local variable, and then we're setting the local variable into here. This might actually be based on this being main. This might be an argv. It's like an argument you actually pass in, but not sure. But hopping into lab, we can see that it's actually printing out the address of main. So like it's just giving us a leak to where the binary is at. Then it's asking for input. Then it's flushing the input and then just asking for a gets, which everyone here should know that gets is vulnerable. You can just send in as much data as you want. So that's kind of actually it for this program. Nice and simple. Good job, guys. Woo! But like it's actually, so at this point, I would say here's our vulnerability. What we need to do now is send in 68 bytes. And then since we're EBX, this is 32-bit, we need to put in bytes to overwrite EBP. So that's going to be another 4 bytes, so 72 bytes. And then after that, since there's no stack cookie check, we just need to send in another 4 bytes to overwrite the return address. And since we know where main is, we can actually figure out the address of anything in this program. And if we look at functions, looks like we have a function called useful gadgets. That's not usually there, so that's interesting. But there should be another one. Check lab owner. So right here, it actually looks like we're opening up the flag that they had, and then if our username is the same as this, it'll actually, and our user ID is leet, it'll print the flag for us. So we could just overwrite the return address to jump here, but that's not what we're trying to, or it is what we're trying to do, but our compares won't actually match because if we actually check the address of lab owner, you go to listing, maybe. There we go. Nope. Lab owner, listing. There you go. It's actually like undefined, so this memory will just be garbage because it's not actually set yet. And we can actually check the references to it to see if it's mentioned anywhere else. Maybe. Lab owner. References, show references to lab owner. So we actually get used twice. One here. Oh, both same function. Yeah. So it's only being used here. So we need to find a way to write to it. And then we'll need to, that'll help us pass the actual checks. So I guess the method I'd go about doing this would be overwriting the return address to jump to the actual location of gets, or where gets is actually referenced from in the PLT, which we're not actually going to really talk about that too much, but that'll allow us to write or call gets and actually and overwrite kind of whatever we want, so we can actually put on the address of lab owner, because that's also going to be static.
Could you just jump to the printf?
We could, but we also want to have we want to open the flag. So we need to start up here.
Gotcha.
So that's pretty much it for that challenge. We also have password 3.
Do deny that.
Oh yeah, this one's actually pretty small, so it doesn't matter. I didn't actually solve this one all the way because I'm not good at math. But here we'll hop into main, and so if you're actually looking just at the assembly, because maybe Ghidra isn't on your computer or it's not working, what you're going to do is pretty much just scan over it all and not just focus on one function or something. So we might say like, hey, it's putzing. Yeah, that was pretty good, wasn't it? It's printing, enter password, and then it's scanfing it. That sounds weird. Scanning in, there we go. Then we're calling this function with our data that's actually being sent into scanf. So if we check this function, it kind of looks like it's just doing a simple loop based on this blue line that IDA kind of uses for loops. And it's doing a move 0 extend and move store something else. I'm not sure what that means. But you don't need to worry about that much. But what we're doing here is that we're adding that value that it's grabbing. So it looks like it's going through whatever string we're sending in and making a summation of our total bytes. So it looks like whatever we send in needs to add to be 229 hex. And then if we pass that, we come down to this function. Where if in here we're actually doing the same thing, but this time with an IML. So we're just multiplying it, excuse me, to find the total, which has to equal this large value, which in 32-bit will be a should be a negative number. So we could try and do this, or we could go on to something else. Any ideas? Recommendations? Good idea. We'll go on to something else.
I put the link in offset.
Oh, sweet. Maybe we'll grab something we haven't seen before. Ooh, binary bomb. Is this just like one binary, or is it just a bunch?
It's just one, but there's different like steps.
Ooh. Okay, so I'm going to open up this in IDOT first, and if it starts to look too complicated, I'll jump to Ghidra, but. So, to dwarf found, that's what? Whatever. So, this doesn't look too bad right now. We got a couple phases, kind of actually a lot of functions going on. They're not usually this many, but we'll start at the top. We're in main. Whoops. Compare EDI, that might be our argc. So if it's 1, so let's not get hung up. So if it fails that, it kind of tells you what we'll need and then exits. So we can just check. We need the input file. Yeah. So it looks like it'll open a file, we send it, and then it'll do some stuff. So the best part about reversing is actually running the binary to actually get a static and dynamic analysis version. It's a little large. Is that good? Can you guys still see that? Good. Let's give it password 3. Mount, downloads, binary, nope. Not sure where that came from. Bomb. So if we try running it, welcome my friend fiendish little bomb. You have 6 phases with which to blow yourself up. Have a nice day. All right, send an input. Oh, we failed.
Killed all of us. Try again. Do it again.
You think it's 1, 2, 3, 4?
Might change.
Maybe it's a 7 instead of 6. No, we were close.
Try again. This guy can't have that many bombs.
So let's hop into phase 1. Whoa, not that one. Phase 1. We never actually saw that printed, so maybe we're missing something. So read line, phase 1. Strings not equal. So it looks like our strings, string length, looks like it just calls or finds the string length of what we passed in. And then we can just check this based on like the name. We can just check to see if these are the same. So let's copy that and try sending it in. Phase 1 diffused. Okay, so that worked. Guessing that just says phase 1 diffused. Nope, there's a secret phase though. Secret phase, what happens in there? Well, now we need to find the secret phase. So, looks like we need to send in 2 numbers and a string. So, if Dr. Evil, for strings not equal to that, anything about the numbers though? Doesn't really look like it. So I guess we just try sending in 1, 2, Dr. Evil. Nope. Maybe that was a... Nope, okay. We're not good enough for the secret phase. That's weird. Number of input strings, 6. Maybe we have to send it all in at once. Oops. Send this in. Nope. And then 1, 2, Dr. Evil. Okay, well. What the heck? Oh, I was copying the wrong one the whole time. Good job, guys. Evil. Well, whatever. On to phase 2. Phase 2 is reading in another line. And then read 6 numbers. So we send in a line and then 6 numbers. Unless it's, yeah, maybe. Yeah, no, it's doing scanf, which is going to be, pretty sure it's slightly different. I think 6. So scanf kind of will do, if I remember it correctly, which we can actually check with the man pages. What? Huh. Oh yeah, I didn't. That was pretty cool. I wasn't expecting that. So scanf, I'm pretty sure, if we can find it, will actually read in from a buffer we already sent in. So we have to send in the line, and then from there it'll do we'll do the scanf stuff to figure out what's actually inside there. So it's kind of like a second stage to reading in a line. So once it reads in our 6 numbers, does it do anything to them? Nothing. So we'll need to then come down here, do some stuff. Looks like we have a little loop. We might just have to run it again, see what we get. Might just be asking for 6. So 1, 2, 3, 4, 5, 6. Was not that. So here I'll start opening up in GDB. So GDB is the GNU decompiler, maybe something. Debugger. GNU debugger. I have it set up to run, not this, right now it's set up for Pwn debug, but I think I might have broke that. We'll try it. But Pwn debug is just another like plug-in to make it look nice. So we'll break at phase 2. Whoops. So we run it, send in our first line, 1, 2, 3, 4, 5, 6. So in here, we'll read in 6 numbers. Looks like we got 6 back, so I'll write in all 6 of them. Compare this to 0. It's not 0, so we should be good. Try to figure out where we are. So now we're going to come here. Move 1, whatever. So it looks like we're comparing the value at RBP to EAX. So EAX is going to equal 2. RBP is not equal to 2. That's actually equal to a number a little bit larger than 2. So at this point, instead of doing a lot of mental math, we can also open up in Ghidra and see what Ghidra thinks.
Yeah.
Yep.
It also has a dragon animation, so
Yeah.
you know it's good.
100% more dragons than Ida.
Yeah.
Analyze that.
Classical paintings, though.
So like this isn't actually like a intro to Ghidra. If you want to do that, they have good walkthroughs and that actually come with it. But when you hop into it, it doesn't actually bring anything up. So I like to press G and then jump to whatever I want, not main. So here we'll go to phase 2. So it looks like do while not equal to 6. So it's going to go through all our stuff. If our variable 1 is equal to ivar 2 plus the address of or the dereference of pivar. So ivar 2 is equal to 1, and looks like it's going to increment, so it's going to be 1, 2, 3, 4, 5, 6. I wonder if they actually messed that up and it's a little bit backwards. So that might be.
I have a quick question.
What's up?
This might sound a little dumb, but does Ghidra interpret that assembly language and give you like that pseudocode?
Yes. So what Ghidra is doing is that they're using some advanced linking and jumping around and figuring out what's actually happening. By looking at the bytecode, they're able to put together an appropriate assumption of what's actually happening.
Okay.
But there's a lot of times where there might be like one instruction that modifies a memory address, and then Ghidra doesn't see it again, so they'll be like, must be nothing. And that's where kind of Ghidra fails, is like in these kind of specific moments where you need to know what's in that memory address, but Ghidra isn't able to help you because they're like, well, it didn't happen again, so why would it even matter? But yeah, so Ghidra does go through it, and then they're trying to give you this source code.
And it's mainly an assumption.
Yeah.
It's not like,
It's not going to be precise,
okay.
but it's pretty good from what I've seen for the most part, except for in some slight one time or in some kind of specific moments. So back to it. So right here, I think is actually one of those assumptions gone wrong. Because right here, it will take EBX, which is the counter. No, maybe it's not. No, okay, so it is right. So what it looks like it's happening is that it's taking our ivar1 will be just a counter from 1 to 6. Pivar1 will be our actual stream that it's going through. So it's checking to make sure the next value is equal to the current value plus 1. And if it's not, explode bomb. So, which kind of makes me wonder why our 1, 2, 3, 4, 5, 6 did not work. So we can actually keep checking GDB. Looks like right here, it's 2 and 2, so it should pass. Okay, then we'll increase it. 3 and 3. Nope, right here we have 4. So comparing 3 to 4. Maybe it was increasing by 2. Increased by 4. That should be right. 6. Huh. So if we run it again, send in our first line, send in 1, 2, 4. Maybe it's doubling every time. 16, 32. Then we'll check that. So we check 2 and 2. 4 and 4. So maybe it was doubling instead of. No, 8 and 7. So did I send that around? What did I send in? Oh, I guess we'll do it again. 1, 2, 4. So maybe it's actually every previous value plus the net current one. So 1, 2. Now that doesn't make sense.
Fibonacci sequence.
Do you think it's Fibonacci?
Maybe.
I think that makes sense for 7. So then 13 or 11, 18. We'll try that. So this is kind of what reversing is. If you can't figure it out just based on the static, it's kind of just like messing around with it until it works. So 1 or 4, 7, 11, which is B. So it is a Fibonacci sequence, which will be the previous number plus the current, or previous 2 numbers will equal the current number. It's kind of a way to look at it. Oh, that's not right. I must put in 16 instead of 18. But we know what it is now. So we can delete our breakpoint and set a breakpoint on phase 3. Phase underscore 3. And that 1, 2, 4, 7, 11, 18. Okay, so it's not liking my 18. Back to drawing board. 1, 2, 4, 7, 11. Let's go 20. So 7, 11. Oh, 14. That's not right. Oh, it wants to be 16 for the last number. That's weird. So, definitely was not the Fibonacci. 2, 4, 7, 11, 15. 16, sorry. Maybe it was the last number plus the current index.
Yeah.
That's what it was. Yep, because it wasn't 1 plus the previous. It was the current index plus the previous. All right. That's my bad. We could have finished this up sooner, but if you guys are here, you obviously don't have anything better to do. Self-roast. So, that's number 2. Keep going. So, there probably is a secret phase, but we're not good enough for those, as we know.
Only good enough to get an IDA Pro license.
That's nothing. I can talk about that too, but... Oh, we got a switch case this time.
That chair is so quiet.
Thick, that graph.
Oh, yeah. Okay, so if we look at this, this is the stuff we like.
Graph.
We have a switch case of seven cases with the default, and then whatever this guy's doing, just hiding out there. So we'll read in 2 numbers, and then based on the switch case, I'll compare it to 7. If it's above 7, we're automatically going to lose. So we're going to load into the first number, and then based on the first number, we're going to do our jump. So what we need to do is figure out what this jump is actually doing. So we're moving EX that, then it looks like we're comparing our second number to that. So if we just set, it doesn't really matter which one we do. So we can do 93 hex. So when you realize 93 hex is not actually the same as 93, so it's going to be 147. So we'll send in 5 and then 47, and hopefully that'll work. 5 and 147. Whoops. So we'll do a quick step through. That's good. Compare EAX to RSP plus 12. So we'll do a quick dump of $RSP plus 0x 12. And it looks like it's 93, and EAX should be 93. So we should pass this one. Break on phase 4. Oh, we're halfway there already. So we'll hop back to IDA for this next one. Phase 4. In here, we're going to do another scanf for 2 numbers. Compare it to 15. If it's below or equal, so that's a unsigned check, so it can't be a negative number either. We're going to come down here, then we'll call function 4 with our first number we actually sent in. Man, these just keep going. Looks like we have a recursive function call. So recursion is where a function calls itself to do a process. So it looks like what this is doing is something that Ghidra will tell us. Function 4. Function 4. So this looks pretty gross. So it looks like we need to rename some variables. What's up?
IVAR3 is my favorite name.
IVAR3, yes. Those ones I don't actually care about. It's more the parameters that's sent in. Because I'm pretty sure... Oh yeah, that's any involvement. So, for some reason, this is just set to 15. Can't call it that. Oh, we can. That's a bad name to have. We'll keep it. 15, and this one's 0. It's also a bad one to have, but it works. This one is first input, or first num, we'll call it. So it looks like it takes our variable 15 and minuses it by our variable 0. So I would not recommend actually naming your variables numbers, because this actually kind of will mess you up if the numbers change now. But we're not going to worry about that. So it takes IVAR1, or, oh, we lost number 3. That's a shame. Rest in peace. But looks like variable 1 will be the current index, which is where our recursion will actually come, because it looks like it's going to call the current function with these values plus or minus 1. So these actually counters will change every time it gets called. because this will help us figure out our current index. So we'll say this will start off at 15, and then probably the next one will be 14, and so on. But then we're going to take that value and shift it right by 30, 31. I guess pretty much it's 32 at this point, because there's also another one. And then we're going to add that. So this is just kind of like really gross math. So instead of looking at that, let's just run in GDB again and figure out what's happening. So we'll send in, let's go 15 and 0. Not to confuse anyone. So I just went past the compare I wanted to stop at. We'll compare RSP plus 8. So this guy right here, which is 0 to 15. If it's below or equal, explode. Looks like we exploded. Can't be equal to 15. That was our first mistake. Oh gosh, what was this one? 1, 2, 4, 7, 11, 16. We can get rid of this breakpoint. Delete 2 and 3 and 4. Oh gosh, we want 5 and 147. So 14 and 14. Let's do that. Okay, so as we can see, we sent in 14. Nope, still saying 15. So that's not very helpful. Weird enough, it worked. Whatever. Oh. RSP minus. Okay, never mind. Next, we'll do some EDX stuff. Looks like it's going to set up the next function call and call the function again. What we really care about is what happens when it leaves the function. So we can find out where it actually returns from this function, which is always going to be right here. So we can just set a breakpoint at this location and explode it in the meantime. So we actually need to figure out what's going on. Yeah. So it does some shifting. Shift right, 1F. Add it. Shift AR. But that shouldn't really matter for what we're working with. Unless it's doing something else I'm not realizing. So. Oh no. I messed up. Overwrote my buffer.
That's not very cash money.
It's not very cash money at all. Which one was it? Phase 1. There we go. So this is where live demos like to lead, is to failure. So I will just fuel that failure and bring you guys on this rabbit hole that I'm now jumping into. 11, 16, 5, 147. Let's actually make a little note of that. Notes. Boom. 1, 2, 4, 7, 11, 16, 5, 147. Okay, keep that. So if we do 14 and 13 this time though, and actually step through it maybe. So weird enough, it's not actually function 4. Oh, that's why. I skipped right through function. I didn't like even step into function 4. It's what we needed. It's my bad. That's what we want. So let's step into it this time, and now we can see that EBX holds 15. But when it shifts right, it's going to become 0. So I'm not really sure what the point of shifting right by is anyways. So now add EAX and EBX. Shift EAX by 1. So 15 now becomes 7. LEA, EBX, EAX, RSI plus So where's RSI pointing to? 0. That is gonna not be good. Actually, no, it's pretty much just another way to do math, is when you just set the register to 0 and kind of pretty much the same way as just moving, in this case, EBX, RAX. It's kind of just convoluted. But we want EBX to equal to EDI. And EDI in this case is 15, but it looks like RBX is 7. That's not what we want. So, actually no, it's just going to go to the next one now. So let's step in there and check that out also. So now we just get into this endless loop of calling these functions until we hit the payload. So keep going. Whoop, I'm lost. Compare EAX to B. So we have 2D instead of B. It's a little bit higher. So it looks like we explode. But what we do know is that the value is less than 15. But I never really saw where the second value came into. So go back to phase underscore 4. It's definitely reading 2 numbers, but does it actually ever use that second number? Alright, so it looks like it just compares that second number to 11, so we don't actually need to worry about it. And then we just need to figure out what number to pass in as the first one that's less than 15, that when going through the function that does some stupid math on it will equal, what was it, 20, or 2, no, to equal 11. So it's obviously not going to be higher than probably 11 because we need to shift it and then add it. So I'm thinking it will be around 4 or something. Yeah, because I think what's happening would be, if my assumption is right, this might be it. Whoops. And for some reason it broke. Run. Okay. So we set that break back at phase underscore 4. Run it. Send in the first payload 1, 2, 4, 7, 11, 16. Second payload of 5 and 147. Third payload of 4 and 11. So stepping through this, we'll call function 1 or function 4. Go through it. And looks like it worked. Nope, maybe not yet. Oh, we're at 13. That was really close. But it needs to be 11, so we failed that. So maybe if we check, so we sent in, so I think what's happening is that it's taking our bits and just keeps shifting them one to the right continuously and adding those values together. So 4 plus 2 plus 1 isn't actually 13 hex. So maybe it wasn't that. But let's head down to 3 and run it again. 1, 2, 4, 7, 11, 16, 5, 147, 3, and 11. Step into it. Jump right past that. Pop RBX, return, compare EAX. Well, that sucks. So close. It's not 3 and it's not 4. What's between 3 and 4? That's right. So, at this point, the best plan of action is to actually figure out what's happening, but since I'm stubborn, let's brute force it. We can do that with a simple binary or simple pwn tools, because everyone knows that's the best. Call it brute.py. Nope. Brute, yep, that still works. From pwn, import everything. P is equal to process. It is called bomb-x64.
Control Z, come on now.
Yeah, it's the best way to hop out of Vim. P.send line, send in our first string. Send a line.
Send it in line.
1, 2, 4, 7, 11, 16, 47, 9. Let's do string of x plus 11, x in range of 15. Interactive PI close. So if this works, oh yeah, so there's 0. That was well worth that couple of seconds I wrote that up with. 16. Oh, not that one. 5 and 147, 0. So if we step through this, was not 0. What the heck?
Does it start at?
What's up?
That should start at 0.
Yeah, it should start 0. That's number 2, halfway there. So you got that one. Try this one. That's definitely new. What if we went to the next one though? Okay, so 1 also worked. That's weird. Let's try with 1. 2, 4, 6, 7, 11, 16, 5, 147. 1. So going here. It still explodes. Oh. It's because I didn't send in the second number. Darn it. So probably 0 did work. 4, 7, 11, 16, 7. So 0 and 11. So going to the function call, we just skip past this time so we know it's going to pass because we're pretty good at programming. And now we're on to phase 5. Let's delete that. Okay, phase 5. So, if we look back at this, to be perfectly honest, I have no idea what's going on, but it doesn't matter because we did know that it had to be less than 15, and that's easily brute forceable. More of the story, there isn't one. But, I really wanted that secret phase, but maybe we'll look at those, but it might just take too long. So, 2 more numbers. So nothing's really changed with phase 5. Number 1 is right here. It's compared to 15, or maybe E is 14. Yeah, F is 15. Anyways, 15. If it's the same as that, we're going to jump down and fail. So it could be anything but 15. That's weird. But right here, we're going to check this array, which has some values in it. Could actually probably set this up, say array. Whoops, not that one. Array of, sure, 8. No, they're not D word, or they're not Q words though. They are array size 8. Oh, it's not letting me change it. Can I just do that? So what I'm trying to tell it is say, hey, instead of actually check to see if they're 8 bytes each, because I'm pretty sure they're 4 bytes each. So right here, boom, 10, 2, 15, 7, 8, 12. Oh, that one's 15, 14. Keep doing that. 11, 0, 4, 1, so on. Oops. So if we go back to the actual function, looks like it goes through there. We'll add them all to ECX. Compare EAX to 15 if it's if it's not 15, it will leave. No, it will continue. Jump if not 0. Yeah. If it's not 15, it keeps going. Else, not really sure where our counter actually comes into this though. Because it's, yeah. Whatever. Oh, it starts off with our current index. So if we actually look into their array again, we want something that equals to F, which is this index. So we go 0, 1, 2, 3, 4, 5, 6. So it looks like our first number has to be 6. Or we could also do this one because it'd add them together. 6, and then we'll move that into there. That doesn't make sense, whatever. Compare EDX to F. So that's actually a bigger problem because EDX has to equal 15, so which means it has to go through this loop 15 times. It's starting to become a pain. It's not like a hard pain, it's just there. 2, 4, 6, 8, 10, 12, 14, 16. So we have enough numbers. But if what I was thinking was correct, which it doesn't really appear to be, whoops, maybe our first number needs to be ECX. Where's that one come from? Oh, that's the total. Oh, okay. So, rethink everything I was talking about. Maybe not. Okay, right here. It's going to grab... No, it's grabbing that again. What the heck is going on? No, like, I think I understand what's going on. I just don't like it. So, what it's going to do is take this array. Whatever we send in as our first number will be the first index it grabs. It'll then grab that number, add it to ECX, and then we have to have this loop go through 15 times. But the catch is, it takes this number, and that's also the next index that we're going to grab. So we have to actually figure out a way to jump around, hit them all, and then on top of that, have it equal to 15 at the end. No, it just goes through 15 times. Oh, we can just start at 0, I'm guessing. Jump to 10, so on. We'll have to check that. But what we really need to do is make sure our second number is equal to all those added together. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B, C, D, E. So it looks like all the numbers are actually there. So I think if we start at 0, we'll jump to index 10, which is 0, 1, 2, 3, 4, 5, 8, 9, 10. We'll go to 1, then we'll go to 2, then we'll go to 15, then we'll go to 5, then we'll go to 12, 15, 14, 13. Yep. Then we'll go to 13. Then we'll go to 3. All right, so I think that should work. We can try this. But what we really need to do is figure out what all those added together is. So we can do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15 plus 6. Nope. 120. Could have done this easier with the actual math behind it, but we're not going to worry about that. So, second number needs to be 120. First number is 0. Try that. Continue. We'll try 0, 120. So, scans it in. Blah, blah, blah. EAX 10. Blah, 4, 5, 6, 7. Oh. So, can't start with 0. So, what we could do is also figure this out mathematically, but we have a pretty good brute force script already running, or already set up, so I'm not sure why we'd really waste that. We can just brute force 15 again to see what index we need to start at. Clean that up a little bit, but this needs to be set to 120. So, not 0, not 1, 2, 3, 4, 5, 6, 7, 8. Oh, no, this wasn't it. Maybe I messed up. Is my math wrong? Oh, unless. Unless it's. Nah, that should be right. Let's change this to 16 because I don't think it actually hits 15. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, that sucks. Any other ideas? Anyone? Because I believe that's what's happening. ECX, add EAX. What's ECX set to? That's 0, okay. EDX1 has to be 15. If EDX isn't 15, we blow up. So it has to go through all 15 times. And then it just compares. Moves our first number, yeah. But into our second number, it would be that. Compare that to ECX. ECX is that, yeah. So maybe I just messed up. Oh, yep, I did. No? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 120. Oh, that's weird. So, let's actually copy this to a text file. Yeah, this won't work. We'll give some new space. Get rid of that. I wanted that actually. So let's make it like look a little bit better to figure out what's actually 13, 11, 15, 12, 14, 10. So let me also index them. So actually be better if we did this. Don't mind all my open files. Personal project. This way we can actually find the index relatively easier, so we can jump around to see what's actually happening. Make sure we have the correct order. Oh no. Darn it, I'm gonna be off by 1, whatever. So, 10 will jump over here to 11, 1 goes to 2, 2 goes to 3, 14 goes to 15, 6 goes to 7, 15 goes to 16, 5 goes to 8, or 5 goes to 6, which goes to 12, which is 13, 3, 7. All right, there we hit 15 twice. So, it actually looks like 15 might need to be the last number. Now it should go through it 15 times. Count me confused. Nope. Yeah, 15 has to be the last number. So, if 15 is the last number, which means 6, so index 6 has to be last. What calls index 6? Index technically 14 because we need a 0 index and we're just off by 1. So 6, 14, what calls 14? 2 does. What calls 2? 1 does. What calls 1? 10. What calls 10? 0. Calls 0. 8. 8 is 4. 4 is 9. 9 is it's gonna 13 is 11. 11 is 7. 7 is 3. 3 is 12. 12. Let's see. 11. Kind of hit a little loop there. I'm not really the happiest about that because that could be a problem. I might have messed up. Yeah, 13 is 11. Oh, okay. It's actually 5. What goes 5? That's 15. I might have totally messed this up, actually. 2, 4, 6, 8, 10, 12, 14, 16. So it looks like all the numbers are there. So it looks like our first number we actually need to send in is 15. Let's try it. Hopefully it works. Nope. Cat our notes. Just copy all that. Oh gosh, we didn't add the last one. 0 and 11. So 15 and then 120. So we hop in here. We'll go through this once. Okay, it was not 15. Didn't like that. What? Why not? Oops, 15 and 120. So it should take our oh, it has to be less than 15. Now that doesn't make any sense. We need 15. So maybe it was 14 instead. So, on phase 5, let's set a breakpoint at that one, plus 93. Break there. Let's just brute force this by hand because maybe our script was off, but I'm pretty sure it shouldn't. No, I still think our answer is supposed to be 15. Or our first index should be 15. But it doesn't want 15 at all because we can't send in 15. So, oh, no matter what, it can only be 15 as a max. Huh. It's weird that that didn't work then. Oh, let's quit that. FG. String of X plus 120. Maybe I was just off on that. But no matter. We can do 0, 120. B, delete 2, continue. Nope. Welcome to the world of reversing. Let's run it. 0, 1, 120. Nope. 2, 120. Nope. 7, 120. We're getting there. We're almost there, guys. I can feel it. Okay. So. Yep, I sure am. Forgot to send in the first data the whole time. So, 1 and 120. 2, 120. Oh, almost missed it again. Oh, he hit it. So 5. 5 was the answer, guys. Good job. It only took us a little bit. So let's make sure that's actually the right. So I thought it was 120, but it looks like RSP plus 12 does not happen to be the value I was thinking. So it's comparing with ECX. ECX is 73, which I'm pretty sure 120 is 78. So we're off by a little bit. So we can actually change that to 73, so 115. Wherever we got the extra 5, it doesn't really matter. But that's probably why our brute force didn't work, is because we had that at 120. Whereas if we changed to 115, it's not really worth it now. But we can fix the notes and say 5 and 115. Oh, so maybe what is actually happening was inside the array was that instead of actually hitting every number once like I thought would happen, it was actually hitting a number twice. So it was actually 5, or it was actually less than the 120. So that kind of makes sense. But not really, because then it would have looped and just got stuck forever. Whatever. So now we can actually delete our breakpoint, set to breakpoint at phase 6, the final phase. Get the notes. Let's see what's going on with it. Phase 6. So you're reading 6 numbers again. And then we got a lot of stuff that's going on. So this is Ghidra?
Maybe.
Probably. That's just like too much to really go through. Phase 6. So read 6 numbers. While true, if 5 is less than the current value at pi var 3 minus 1u, that just is kind of a weird way Ghidra sometimes interprets the numbers. So it's just 1. You don't really need to worry about it. But pi var 3 is equal to local 78. Local 78 is equal to just an array. Not really sure what that's going to mean just yet, but we'll figure it out. So let's kind of rename that to, come on, maybe we won't rename it. Pi var 3. There we go. Let's call it array or something. Whoa. Just move that whole thing. Alright, anyways. So, we'll check ivar 5 plus 1. Ivar 3 is equal to ivar 5. If it's equal to 6, we'll break out of our loop. So when you go through all 6 numbers, it looks like. So we can just call this counter. And just to make it simple, since ivar 1, we'll call this counter 2. Electric Boogaloo. So, it looks like it's kind of doing a double for loop just based on this. So the first for loop would be 1 through 6, and then the second for loop would be the I of the first for loop to 6. So we can kind of see here that pi var 1 or 4 is equal to the array that we're using up here at the second counter's position. So we can set this to, so if it's equal to that at all. Oh, interesting. But does pi var 4, oh, yep, pi var 4 increases. So it looks like, just off like current speculation, it's looking to see if any of the numbers are the same at first. So if we send in 6 numbers that are all different, we should possibly pass this. I think that's good enough for that part, so let's go to the next one. Gosh, this is a huge function.
Probably take too long.
It might. It's been an hour and a half. So,
Exercise for the
yeah,
reader.
exercise for the reader. Let's just make sure we actually got that right. So 1, 2, 3, 4, 5, 6. We'll disassemble it. We actually just want the location at after the first loop, which looks like it's right here in this area. So we'll just set right here. So at 1 or 40, go to listing. We have this address. We can copy that. Set a breakpoint there. This will just tell us if we're right on the first part or not. Continue. What? IB. Delete 5. Oh. They just read that as a number instead of hex. Let's try that again. 0x. Oh my gosh. 0x. Continue. Continue. Oh wait, no, that was it. So boom, we did get the first part. So all 6 numbers had to be different. And if you look, like, if you squint really hard, this says phase 6 completed. So this kind of went on a little bit longer than I was thinking, but hopefully you guys learned something. If you have any questions, I'll answer them.
A little off topic.
Yeah.
Your background on IDA to be dark.
Yeah, so if what I did was searched IDA dark theme,
Okay.
and then you find out, hey, you need pro version to actually get the plugins to do that.
Dang.
So I think there was actually a way to get, it's like that, you need a plugin for that, I believe. Unless it's just this. Oh, it is just this.
Okay.
So you take in this file, so here I'll do it like a live demo kind of thing. So I'll just toss this onto the desktop.
That's a lot of windows.
I think that's right. We'll do a file save as to desktop. We'll call it dark.csl, I think it was called.
CLR.
CLR. Yeah. CLR. Then we can go to IDA. Pretty sure it's underneath colors. Import. Then you can import any one you want. Actually, I think I am using that one. It's just not. But we can find out. Okay. Yeah, I must be using that one. But it's weird that that's as dark as it got. Oh, yeah. That's where it's really black.
Oh,
So this is the exact one I want. Or am using. I can toss this into Slack if you want it.
yes, please. Also, what's the difference between like a keyword and D word?
So a keyword is just 8 bytes, and then a D word is 4 bytes.
Okay.
And then there's also a byte, and then a word, which would be 2 bytes. A nibble, which is a bit? No.
That's 4
I think it's 4 bits, yeah. So it's just kind of a different way to reference memory.
Okay, got it. And that's like allocated whenever somebody says like int or.
Yeah, so like with 60, so an int by definition is 4 bytes. A long, depending on the implementation, can be either 4 or 8. But usually like, so in 64 byte or in 64-bit binaries like this one, where it's like all the registers are 64 bytes, so they're going to be referencing D words or Q words more often. And then if they're not, they'll reference it like, they'll just reference the 32-bit register if it wants the D word instead. Yeah.
Got it. And last question. In ARM, you were saying like the labels are different and it goes from R0 to R15. Are those kind of the equivalent to like EIP, EAX?
Yeah.
ESP?
So if I go back to, I guess the slides don't really matter, but so when I said R0 through 15, so like R15 is the instruction pointer, so that'd be the same as EIP or RIP. R13 is the stack pointer, so that'd be the same as SP and Rs. So they pretty much kind of link one to one, but and I like a lot of times they'll reference those directly as instruction pointer or stack pointer, but there's also a lot of times it'll be like R13, R14, R15, and it's like you could move a value into those, but you probably shouldn't because you'll break the program. Yeah.
Okay. Thanks.
Yeah, no problem. Let me toss that into. I'll just toss it in OffSec.
I'm just gonna end the stream.
Okay.